If you've ever jumped from Node.js into the world of Rust, you've probably had that moment. You know, that feeling that even for something as fundamental as async programming, you've landed on a completely different planet. So let's dive in and figure out why these two async worlds feel so incredibly far apart. And yeah, that brings us to the big question, right? Async is pretty much the backbone of any modern web service. So why on earth does Rust make you pull in a whole separate library like Tokio, when in Node.js, async and await just work, straight out of the box? It feels a little weird, but the answer tells you everything you need to know about the core philosophy of each language.
To really get this, you got to think of it in two different ways. On one hand, you've got the batteries included model, and on the other, you've got the bring your own model. Honestly, this one little analogy is the key to the whole thing.
Okay, so let's start with the familiar stuff. In the world of Node.js and TypeScript, you write an async function, and you just don't think about how it runs. You just write the code, and you trust that the Node runtime is going to handle all the messy details for you. It's easy, it's fast to write, and you can be super productive. And this right here, this is the absolute heart of the difference. See, Node.js isn't just a language interpreter, it is a runtime. It comes pre-packaged with a whole shebang, an event loop, a task scheduler, all your async I/O. But Rust is just a language. It gives you the keywords, async and await, but when you compile your code, there's no engine included to actually run that async code. So if Rust doesn't give you a runtime, how does any async Rust code actually run? Well, this is where you have to bring your own. You need to add that engine yourself. And for pretty much everyone, that engine is Tokio. Tokio has become the standard async runtime in the Rust world. You can basically think of it as the event loop, the scheduler, and all the async magic that Node has built in, except it's a library that you consciously choose to add to your project. It's the puzzle piece that fills that runtime gap we just talked about. And it gives you a ton of stuff. We're not just talking about a simple function executor. You get a super optimized scheduler built to handle like hundreds of thousands of concurrent tasks. You get async versions of all your networking and file system tools. It is a complete, powerful toolkit for building seriously high-performance systems. Which, of course, makes you wonder, why? Why would Rust creators choose a path that seems to add this extra layer of complexity? Well, it all comes down to one of Rust's most fundamental principles, the philosophy of zero-cost abstractions. This idea, which Rust borrowed from C++, has two simple but really powerful parts. First, if you don't use a feature, like, say, an async runtime, your final program shouldn't have to pay for it, not in size or in performance. This is huge for stuff like embedded programming. And second, if you do use a feature, the nice, high-level code you write should compile down into machine code that's just as screamingly fast as if you'd written it by hand in the most optimized way possible. Okay, here's a perfect example. Look at this code. It's using iterators, it's clean, it's expressive, it feels really high-level, and honestly, it's just a pleasure to write. But this is where the magic happens. The Rust compiler takes that beautiful, abstract code and, well, it transforms it into this. It becomes a super efficient, tight loop with no extra overhead, no hidden memory allocations. It's the exact same performance you'd get if you were a low-level coding wizard writing it by hand. You get to write the pretty code, but you get the performance of the gritty code. Best of both worlds. And that's the absolute key takeaway. In Rust, these amazing abstractions are basically a compile time illusion. By the time your code is actually running, they've been compiled away, leaving behind nothing but hyper-efficient machine code. There is no secret performance penalty for writing clean, high-level code. But listen, zero cost doesn't mean no cost. It just means no cost at runtime. This philosophy comes with a very clear set of trade-offs. That cost has to be paid somewhere, and it's not paid by the CPU. So where does that cost go? Well, because the compiler is doing all this incredible optimization work, your compile times get longer. The language itself gets more complex. You have to wrestle with concepts like the borrow checker, lifetimes, and traits. And yeah, the learning curve is definitely steeper. The cost is shifted from the machine to you, the developer. This table really lays it all out. Traditional systems like Node give you simplicity and developer speed by adding some overhead at runtime. Think garbage collection. Rust does the opposite. It gives you raw, bare metal performance and total control, but you pay for it up front in compile times and learning complexity. You choose Rust when that nanosecond level control is what matters most.
All right, enough with the theory. Let's make this real. Let's look at probably the most common async task in the world, just making a simple API call.
On the left, you've got your classic TypeScript. It's short, sweet, looks totally familiar. On the right, the Rust version using Tokio. Okay, it's a bit more wordy, you've got more explicit error handling, but it does the exact same thing. The real difference isn't what you see here, it's what happens under the hood when you run it.
So, when the TypeScript code runs, the Node.js runtime is creating promise objects, it's allocating memory, and a garbage collector has to come along later and clean it all up. The abstractions are still there doing work. But the Rust code? The compiler has completely transformed it. That async function has been turned into a super lightweight state machine. It's just a tiny little object that tracks, am I waiting for the network or am I done, with almost zero overhead. The abstractions have literally vanished.
And the difference is just huge. You've got Rust's compiled state machine versus TypeScript's runtime promises. You've got minimal, predictable memory usage versus a garbage collector. All this means way lower overhead and much more predictable performance for Rust, which is exactly why you'd pick it for a critical service that has to handle tons and tons of traffic without breaking a sweat. If you only remember one thing from all of this, let it be this slide right here. It's the perfect summary. TypeScript's philosophy is, let's do more work at runtime to make life easier for the developer. Rust's philosophy is, let's do a ton of work at compile time to make the runtime as fast as physically possible.
At the end of the day, neither one is better. They're just different tools for different jobs. One is designed for rapid iteration and developer convenience, and the other is engineered for absolute, uncompromising performance. So, for your next project, what are you going to reach for? The batteries included ease of use or the build your own raw power? The choice is yours.